Hello everyone, this is Swati Shastri taking a session on computer networks and security. So in the previous lecture we have actually learned about public key cryptography, wherein there are two keys and one is public key and one is private key. Public key is used for encryption and private key is used for decryption. So under that we have learned an algorithm that is called as RSA algorithm, that is revert, Shamir and the HELLMAN algorithm, wherein we were producing or generating keys, exchanging the keys, and we have seen how to encrypt and decrypt the data. So today we are going to learn one more kind of a protocol, and that is called as DIFFIE-HELLMAN protocol, and this is especially meant for key exchanging. Okay, so whenever you have a symmetric key or a public key of your RSA should be exchanged with each other, that is the sender and the receiver, that time you make use of DIFFIE-HELLMAN key exchange protocol so that you can exchange these keys. So this also comes under public key cryptography, but it is a quite a different concept. You don't have like public key and private key. There are assumptions on which the DIFFIE-HELLMAN works. So what is Diffie-Hellman key exchange and why is it required is our question on this. So when you consider this Diffie-Hellman key exchange, this was the first method which was which was developed for safely exchanging the keys, even when you have an insecure kind of a channel. When you are having an insecure kind of a channel, you should be exchanging keys so that you should not leak your data. So for that reason, we came across Diffie-Hellman, which helped us in exchanging the keys. Consider that you're a spy and your work is to send information to the client, whatever you have learned. Now, how can you send information to your client? You can send information in two ways, right? Either you personally go and meet him and give him the information that he wants, or you can encrypt it and send it, right? So why are we taking an example of spy? Because you're not just sending a letter, you're sending the details which are secret enough, correct? So how are you going to send the secret data, especially the keys? When you want to send from one place to another, they are the secret keys, right? So you should maintain that secrecy. For that reason, you make use of something. So I can either go personally and I can give it to him, or the only way is that I can have an encryption algorithm in such a way that it will keep my secrecy or privacy without any indulgence. Now, what is this way of sending? Either I can encrypt it, I can take the key, I can encrypt the key and send it to the sender, right? If whenever you want to consider an example of symmetric key, there is only one single key present between the sender and receiver. Sender has to send that particular key to the receiver. Now I can encrypt that key and send it. But to encrypt the key, you want one more key for the sake of encryption, correct? So when you want that one more key for the sake of encrypting the present key which will be used onto data, you need to exchange that key. If you know that key, then the new key will be disturbed, correct? So this kind of things will create a problem. Or you can encrypt it using shift ciphers. What is the meaning of shift cipher? Consider that A, wherever there is A, it will become B. Wherever there is B, it will become C. Wherever there is C, it will become D, and so on till Z will become A. So this is completely shift ciphers. I can exchange by this way also. How do you exchange by shift ciphers? If I say let's get dinner, it will become such kind of a message. So you have successfully encrypted it, no doubt, but the receiver and the sender should be knowing that A has become B, B has become C, C has become D. So such kind of things are known. Now this key should be known to someone, right? Now what will be the alternative way for this? There should be something which is going to help you out, right? So there came with the encryption itself, but you're not going to send any encrypted data. Rather, you try to follow up something and you come into a common thing. So that was being given by your Diffie-Hellman key exchange. Okay, these two are the mathematicians again. DIFFIE is different and HELLMAN is different. They both are mathematicians who formed this particular kind of key exchange. Now, where is this DH key exchange used? Basically, the main purpose of using this DIFFIE-HELLMAN key exchange is to securely develop shared secrets that can be used to derive keys. Okay, whatever shared secrets are there, like public key you want to send or your secret symmetric keys you want to send, these things if you want to share, that time you make use of Diffie-Hellman key exchange. So these key exchanges can then be used with the symmetric key algorithms to transmit information in a protected manner. So you can use this in the symmetric algorithm so that you can send your keys in a very protected manner. Or symmetric algorithms tend to use to encrypt the bulk of the data because they are more efficient than the public key algorithms usually. So, or you can technically use this Diffie-Hellman key exchange to establish public and private key relationship. Okay, so in practice, we can see that RSA tends to use this, and there are very many other algorithms also which use this, because this is because that RSA is also capable of signing in your public key certificates, while Diffie-Hellman key exchange is not able to do that. The major role wherein your Diffie-Hellman plays role is your Elgamal algorithm, so which was used in PGP. This is based on Diffie-Hellman key exchange only, so that the protocol that uses it effectively implements that particular kind of Diffie-Hellman algorithm. So there are very many places where you use Diffie-Hellman. You have used Diffie-Hellman even in the virtual private networks, because you can secretly exchange contents on some kind of an exceptions. Like, how is it actually going to work? You can see this diagram. How is it working? Now there is Alice and there is Bob who wants to exchange some information wherein they have to come into this common thing. So consider that Alice and Bob have a agreement on the common paint, like both are have agreed on to yellow color. Okay, so Alice has her own secret color and Bob also has his own secret color. So Alice's secret color is orange, rather Bob's secret color is light blue. Okay, so when Alice mixes yellow with orange, it turns out to become light brown, correct? Rather, at the same time, what Bob will do, Bob will mix yellow with a blue, that is light blue color. That time he will end up with in getting some a sky blue color, correct? So this is the genuine thing that happens with the colors also. Now what will Bob do? Bob will send this glass of water of blue color to Alice, and Alice will send this light brown color of water to Bob, right? So this is under public transport. So according to public, what it is, Alice is sending brown and Bob is sending blue, right? Light blue. So the assumption of that mixture separation will be quite expensive. We should be going with proper exceptions, right? So what is happening here? Now Alice has selected her private color to be orange and Bob has selected his private color to be light blue. Now what happens? Bob has sent sky blue to Alice. Now Alice has orange. What she will do, she will mix this orange with the sky blue color. Rather, it will end up with a light green kind of a color, right? A kind of a green, probably green kind of a color. And when you see towards Bob, Bob also almost has a light brown, which is very nearer shade to your orange, and he has a darker shade of blue. When he mixes almost green kind of a color, he will usually get it. So what is happening there? You have exchanged, according to public, you have exchanged brown and blue, but when you mix out with the secret colors and check it, you will get a common secret color that is green onto both the sides. So this is what is happening. even in your Diffie-Hellman key exchange. So what is happening here is usually in your Diffie-Hellman key exchange, you have two people. So each of them will be having their own secret codes, and there will be one something which is in common. So when you have that, you can exchange any of the information which can be kept as secret. Okay, so it is usually the Diffie-Hellman is usually used between two users. So let us go through the algorithm so that you can understand. Consider that there are two users. Suppose that user 1 selects a prime number A and a random integer x1 which is prime and a generator G. Okay, what he has to do is, now he is having A, user 1 is having A, x1 and G. Okay, now this A and G are the common things between user 1 and user 2. The user 1's secret color is nothing but x1. Okay, A and G are considered as yellow color, which has been agreed between user 1 and user 2. Now user 1 with this particular yellow color A and G and his private color x1, he will try to find out y1. Okay, how will he find out y1? Y1 is always G raised to x1. G is generator raised to x1, which is the private number, mod A, which is the again your LO, which is common one. Okay, now user 1 has calculated y1. At the same time, there are two end users, right, who have agreed on A and G ahead of time. So there is user 2 who is going to perform the same function and creates y2. How is he creating y2? He uses G and A as it is. So y2 will be calculated as G raised to x2. x2 is the number which is a secret number for the second user in the Diffie-Hellman. So G raised to x2 mod A. G and A are the things which are in common to both the user 1 as well as user 2. Correct? So now what happens is, user 1 who has calculated y1 will send this y1 to user 2. User 2 who has calculated this y2 will send this y2 to user 1. So user 1 is getting y2 information, user 2 is getting um, y1 information. So when user 1 has sent y1 to user 2 and at the same time user 1 will receive y2 also, what is his work? His work is to generate key k1 using the partner's information, that is y2. So what you will do, k1 is equal to y2 raised to x1. Remember that this is user 1. User 1 never knows what is the value of x2. He will be only knowing what is the value of x1. So y2 raised to x1, which is the private number of your user 1, and mod A, if he does, he will get the key value, that is k1. At the same time, user 2 will find out k2 because user 2 has received y1, correct? So what he will do, how will he find out k2? K2 is equal to y1 raised to x2 mod A he will do. So that time he will get k2 value. When he gets this k2 value, definitely k1 will be equal to k2. Let us see the example so that you can understand better. When you see this example, what we are trying to do is we are trying to demonstrate the key exchange wherein they are same in the Diffie-Hellman key exchange algorithm, where A value is 5 and G value is, sorry, A value is 3 and G value is 5. So what is given? The given is A value is 3 and you have given that G is 5. We have learned that yellow is the base color for both of them, correct? So A and 3, that is A value and G value, are known to both of them. Now what you have to do to find solution? First you will do assumption. What is that assumption? On user 1, you will assign x1 value to be 5. Okay, this is assumption. Remember, this should be prime number. This is assumption. You can choose any of the number. We prefer to have prime numbers because prime numbers can work vice versa. Okay, so what you are doing, x1 is equal to 5 at user 1 and x2 will be 7 at user 2. You can choose any other number. This is chosen by the user itself. Okay, so when x1 is chosen as 5, now user 1 has to calculate y1. What is the value of y1? Y1 is equal to g raised to x1 mod a, correct? So now when you substitute, what you will get, y1 is equal to g value is 5, 5 raised to x1, x1 is how much? 5, right? So 5 raised to 5 mod 3. Now 5 raised to 5 is 3125, correct? 5 raised to 5 you will get 3125. Mod 3 if you do, you will get 2. How are you getting 2 now? So let me restart this so that you can understand it better. Okay. So what is the value that you have? You have 3125. 5 raised to 5 is 3125. Mod 3 you want to do. So when you consider 3125, 3125, if you divide this by 3, you are getting it as 1041. So what you will take, you will consider only this one, 1041. So when you consider this only 1041, how much you will get? 1041 into 3 if you do, you are getting it as 3123. So this is 3125. 3123, 3125 minus 3123 will be 2. That's why you have got this as remainder as 2. Okay. So similarly, what will user 2 do? So user 2 is actually calculating y2. Okay, this is user 2, sorry. So user 2 is actually calculating y2. How will you calculate y2? G raised to x2 mod a will give you user y2's value. So what will be the, on substitution, what you will get? Y2 is equal to 5 raised to 7 mod 3. Why? Because x2 is 7, correct? So because x2 is 7, if I substitute 7 over here, you are getting 5 raised to 7. 5 raised to 7 is this value and you will get 2 as your mod, correct? Next, what you are getting? User 1. What he is doing, he is exchanging it with user 2. User 1 is sending it to user 2. User 1 is sending it to user 2. Now user 2 will send y2 to user 1. Now user 1 is having y2, user 2 is having y1. So user 1 using y2, he has to calculate k1. So what is k1? K1 is equal to y2 raised to x1 mod a. X1 is coming from the same user. So when you substitute, so what will be k? What will be k1? K1 is equal to y2 x1 mod a. So what is the value of y2? Y2 is 2. X1 is 5. Mod a is 3. So when you do 2 raised to 5, you get it as 32. 32 mod 3 will be 2. Correct? Now, on the same grounds, when you consider user 2 has to formulate k2. How will he formulate k2? K2 is equal to y1 raised to x2 mod a. So when you substitute this, k2, how much you will get? Y1 is 2, right? Y1 is 2. 2 raised to k2. K2 is 7. So 7 mod 3, that will be 128 mod 3. You will get 2. So what is happening? K1 is also 2, K2 is also 2. So definitely K1 and K2 you will get it as equal. So these two things will be considered. That is, K1 will be considered as secret key for user 1 and K2 will be considered as secret key for user 2. So this is how DIFFIE-HELLMAN is helping us. So what has happened after performing these things? You are getting same keys. It means that you have almost exchanged the key, right? So this is how your DIFFIE-HELLMAN is going to work. So just to summarize things, DIFFIE-HELLMAN is basically used for exchanging keys. You have a specific algorithm which exchanges the keys, wherein you agree on two variables, that is a and g value. There are secret keys at both the users x1 and x2. Using the um, using the secret key as well as an agreed upon value, you always calculate y1 and y2 in respective users and 1 and 2. So in user 1 you calculate y1, where y1 is equal to g raised to x1 mod a, and In user 2, you calculate y2. y2 is equal to g raised to x2 mod a. Y2 is sent to user 1 and y1 is sent to user 2. Using y1, user 2 will calculate k2, and using y2, user 1 will calculate k1. So always k1 is equal to y1 raised to, sorry, k1 is equal to y2 raised to x1 mod a. Rather, you will get the second value with the y1, that is k2 is equal to y1 raised to x2 mod a. So with this, wherever you have k1 and k2, k1 and k2 will be equal to each other where you have exchanged your keys. This is how your Diffie-Hellman is always going to work. Okay, thank you.